Okay, so in this problem we're looking at a strong acid and a weak base neutralization. These are more complicated than strong acid, strong base neutralizations, as you might expect. We're still going to start out looking at the neutralization. Well, yeah, we'll start out looking at the neutralization reaction itself. But you'll see with the way we have to work forward in this question, we have to take into account the fact that there's an equilibrium that we're forming, which makes things more complicated. So here we're forming HF and sodium chloride. So that's our acid. Here's our base. And they come together over here, as you expect with an acid and base. And then we also form a neutral salt. So the salt here doesn't really make much of a difference in terms of what we're worried about here, which is the pH of the solution. That's kind of what we're trying to drive towards. Yeah, let's see. How do we want to work this problem? So we want to start by making concentration, or taking it out of the concentration units and into moles. So for HCl, so let's look at HCl. So HCl is just, to do that, we're just going to take the concentration of HCl, which is 0.1, and we're going to multiply that times the volume there. And I'm just going to do that on the side here, just to preserve some space and speed things up. So we have 0.01 mole of HCl. Again, I'm calculating that from this piece here. If that's not clear how we do that, go back to one of the earlier videos and look at how we do it. And now I'm calculating the concentration of sodium fluoride that we have. I'm sorry, the number of moles of sodium fluoride there. So I'm going to take 0.1 and I'm going to multiply that times 30 times 10 to the minus third. And so I see that I have 0.003 mole of sodium fluoride here. Okay, so in the strong acid, strong base problems, we just subtracted one number from the other, and then we were pretty much done with the problem once we calculated concentrations. Here, the things get a little bit more complicated. So at the beginning of the reaction, if we want to kind of write out like a, I'm not sure for sure exactly the easiest way to do that. If we try a rice table. But we're going to call this isn't really like equilibria necessarily that we're worried about down here. It's just the end of this reaction. So we're still working on stoichiometry here. So we start out with 0.001 mole of this, and we have 0.003 moles of this. We have none of this, and we have none of this. And so the change in this, we're going to kind of follow a similar logic as last time. We just need to subtract. We know at the end of this reaction, so these things react in a 1-to-1 ratio. So whatever the smaller number is, we're just going to subtract that from both things on this side. So we have minus 0.001 of that, minus 0.001 of that, and we're going to gain 0.001 of HF and 0.001 of sodium chloride. And so at the end of the reaction, I've been careful here to write end and not equilibrium. We have 0 HCl, we have 0.002 moles of sodium fluoride, and we have 0.001 moles of hydrofluoric acid. And we also have 0.001 moles of NaCl. So I'm using a rice table here. You notice I'm not using equilibria or anything like that. It's just a bookkeeping method to keep track of things. This is just me working through the stoichiometry and using this familiar tool to you guys to do so. But so the important thing to recognize here, that what we want to kind of highlight at the end here, is we want to look at what's in solution that could affect pH. And so this does not have any effect on pH over here. We're not worried about sodium chloride at all. That doesn't matter. you'll notice we have no HCl left. So this doesn't matter either. What's dominating in this reaction at the end of it is the sodium fluoride and the hydrofluoric acid. And so the thing to recognize here is that this is a base, or maybe the right way to say it is a conjugate acid base pair, and it's a weak conjugate acid base pair, unlike this, which is a conjugate acid base pair, but it's strong. But since it's a conjugate acid base pair, then to calculate the pH, I don't have to worry about dealing with the equilibria. So I could do this with a rice table, right, and make things, and we could do it, but it'd be challenging. So you could go in and write out an expression for NaF or HF and write out an equilibrium expression and solve using Ka or Kb, like we do minus x, plus x, that kind of thing. But much easier is to just take and realize that the pH is going to be equal to the pKa plus the log of the concentration of sodium fluoride divided by the concentration of hydrofluoric acid. And so you're given the pKa of HF at the top here. And so this becomes the negative log of 7.2. So our pKa, which I'll write up here as well, is just equal to 3.14. And so this expression becomes 3.14 plus the log of sodium fluoride concentration and HF concentration. So it's important to note here that we're not looking at moles of NaF and, oops, I'd use we're not looking at moles, we're looking at concentrations. So it's a good idea to turn these back into concentrations here. So what's our concentration of sodium fluoride? It's going to be the number of moles divided by our total final volume. So 30 milliliters plus 10 milliliters. Because I've taken a solution and I've made it, I've taken 10 and 30, so my total volume is going to be 40 milliliters. So 40 times 10 to the minus 3 liters. And so that ends up being 0.05 molar of sodium fluoride. And my HF concentration I take this number, 0.001, and I divide that by 40 times E minus 3, and we see that's exactly half, which is what you'd expect because it's half the number of moles in the same volume, 0.025 molar HF. And so we can plug those values in over here, and we can say, okay, our sodium fluoride value is 0.05, and our HF concentration is 0.025. And we come out with a pH that is slightly above the pKa there. So log of 0.05 divided by 0.025 is 0.3. And so our pH is equal to 3.44. And so we've answered the question, sort of, I don't know if it's counterintuitive. I guess it's counterintuitive. This is the situation in which we have excess weak base. But you'll note that the pH is actually acidic. And this is just because you're dealing with such a weak acid, such a weak base, that even though you have excess weak base, the acid still predominates at equilibria. And this is, if you look at the Ka for the acid, it's 7.2 times 10 to the minus 4th. That means the Kb is going to be somewhere around 10 to the minus 10th. So the base is extremely weak, much weaker than the acid. So the pH sort of comes out sort of counterintuitively, but this is just how weak acids and weak bases work. In a strong base problem, this wouldn't make any sense. But here, because it's a weak base, you can still have excess weak base present and come out with a pH that's below 7. So don't let that weird you out. So what is the pH of a solution made from some amount of HCl and a weak base? If the key thing to recognize here is that if you're adding some acid, you have to add some acid. But if you add some acid and it doesn't consume all of the weak base, at the end of the reaction, you're going to have some weak base left over, and you're going to have formed some weak acid. So if I have a weak base and I have its weak acid present, I have a weak acid conjugate base pair. That allows me to use the Henderson-Hasselbalch equation. So excess weak base means we use Henderson-Hasselbalch. Okay, in this next example, we're looking at a solution where you're at the equivalence point, so you've done a complete neutralization. So I can write out this sort of faux rice table again, just as a bookkeeping method, just like the normal rice table, but now I'm not using it for equilibria. So again, I start out with, I want to calculate the number of moles of acid I started out with. Let's see, so I start out with 0.03 moles of sodium fluoride because that's the same as the last problem. And then I also have 0.003 moles of HCl. This is the same calculation as for the NaF. And this makes sense because I'm taking 30 milliliters of one thing at one concentration and 30 milliliters of another thing at one concentration. I'm going to end up with the same. It's not surprising that I end up with the same number of moles. Okay. So at the onset of this reaction, I have 0.003 of both the strong acid and the weak base. The change is going to just be 0.003 for both of them. I'm going to consume all of that. But I'm also going to form 0.003 HF and 0.003 of sodium chloride. So at the end of this reaction, I form some HF. I have no sodium fluoride and I have no HCl left. So what things can affect my pH here? Not the sodium chloride, because it's a neutral salt. Not the sodium fluoride, because there's literally none there. And not the HCl, because also there's literally none there. So the only thing I have to worry about here is HF. And so this is what we'd say, like, sometimes the question will be worded complete neutralization. In titrations, when you're dealing with the situation, you're at the equivalence point. So I'm going to use the term equivalent acid. Let's say equivalent strong acid strong acid, weak base. And this is in terms of moles. So at the end of the neutralization reaction, this is just a situation where I have none of this and none of this. So I've added equal amounts of that. So if it was a strong acid, strong base situation, your pH would just be equal to 7. But it's not that situation. And we have to take into account the fact that we formed HF over here. So I'm going to put this in bright green. So this is the conjugate acid of a weak base. And so we have to account for this. So now our problem is like saying, well, what is the pH of a particular concentration of HF? And so we'll take the concentration of HF that we have, which is just 0.003, and we'll divide it by our total volume, which is 60 milliliters. And we'll get 0.05 molar HF. And now we can use this to solve this problem. So we set up a normal equilibrium problem. So we can't use the Henderson-Hasselbalch equation here because we don't have any of the conjugate base present. And so that the Henderson-Hasselbalch equation is an approximation. It works well when you have both the conjugate acid and base present, which was our situation. Here it is not our situation down here. So I have to work this out in the standard Rice table way. This is really wordy. I'm just going to call this equivalent. Okay. So yeah, so when we have equivalent moles of strong acid, weak base, we can't use the Henderson-Hasselbalch equation. We have to use a Rice table. And so we just set it up like this. We say, okay, we're starting out with 0.003 moles of I converted to concentration. We want to work in concentrations here. 0.05 molar HF. And that's going back and forth. It's going to form a little bit of H+. We're expecting things to be acidic. How much H+ do we start out with? None. How much F- do we have here? None, because that's all reacted with the acid, the HCl. And now we just set this up as a standard Rice table problem. And so we're given Ka at the beginning here. We say that's equal to 7.2 times 10 to the minus fourth. And that's going to be equal to x squared over 0.05 minus x. And we'll do the approximation. So we'll say that that's 0.05 minus x here. We're going to discount. We're going to say that this probably doesn't matter. And so we find that x is equal to 0.006. And so it is much smaller than 0.05, so our approximation holds. And so this is also equal to, let's see, I'm running out of space here. I'll just do this little thing. X is also equal to, so x equals 0.006. This is equal to our H+ concentration. So this is 0.006 molar. And so our pH is just equal to the negative log of 0.006. So 2.2.